Hello students, welcome back. In this animated presentation, we will study Faraday's laws of electrolysis and solve a few numerical problems based on these laws to understand them clearly. I am Aditya Vardhan, creator of adichemistry.com from Warangal. Before discussing Faraday's laws, let us first understand what electrolysis is. Electrolysis is the process in which an electrolyte is decomposed by passing an electric current through it. This is done by applying an external electromotive force. For example, consider an electrolyte AB which dissociates into A plus and B minus ions in solution as shown on the screen. During electrolysis, the B minus ions migrate towards the positively charged anode and undergo oxidation to form B. The A plus ions now migrate towards the negatively charged cathode and undergo reduction to form A. Now, an important question arises: how much of A and B are formed at the respective electrodes? According to Faraday's first law of electrolysis, the amount of substance M deposited or liberated at an electrode during electrolysis is directly proportional to the quantity of electricity Q passed through the electrolyte. The quantity of electricity Q is measured in coulombs. Mathematically, this law can be written as M is equal to ZQ, where Z is the electrochemical equivalent of the substance. Since the quantity of electricity is given by the relation Q is equal to CT, where C is the current in amperes and T is the time in seconds. The expression for Faraday's first law can now be rewritten as M is equal to ZCT. If Q is equal to 1 coulomb, or equivalently C is equal to 1 ampere and T is equal to 1 second, then the mass M becomes equal to Z. Therefore, the electrochemical equivalent can be defined as the amount of substance formed at electrodes when 1 coulomb electricity is passed through the electrolyte, or it can also be defined as the amount of substance formed at electrodes when 1 ampere current is passed through the electrolyte for 1 second. Now let us introduce one more important concept known as Faraday. Faraday is defined as the amount of electric charge carried by 1 mole of electrons. Mathematically, 1 Faraday is equal to charge on 1 electron multiplied by Avogadro number Na. Upon substituting the values of charge on 1 electron and Avogadro number, we get 1 Faraday is equal to 96,500 coulombs approximately. Thus, Faraday represents charge on 1 mole of electrons. Now let us see what is meant by equivalent weight. Equivalent weight is defined as the amount of substance formed at an electrode when 1 Faraday of electricity is passed through the electrolyte. It is represented by the symbol E. From Faraday's first law, we know that M is equal to ZQ. If the quantity of electricity passed Q is equal to 1 Faraday F, then the mass M becomes the equivalent weight E. Rearranging this expression, The electrochemical equivalent Z can be written as Z is equal to E by F. Now, upon substituting the value of Z into the equation derived from Faraday's first law, we obtain M is equal to EQ by F. This relation is very important as it directly connects the mass deposited with the equivalent weight and the quantity of electricity passed. This expression will be extremely useful in deriving Faraday's second law of electrolysis. Now consider that two different substances A and B are formed when the same quantity of electricity Q is passed through their respective electrolytes. The masses of substances A and B deposited at the electrodes can be written as Ma is equal to EAQ by F and Mb is equal to EBQ by F, where EA and EB are equivalent weights of substances A and B respectively. Since Q and F are constants, the ratio of the masses Ma by Mb is equal to Ea by Eb. Thus, when the same amount of electricity is passed, the masses of substances deposited are proportional to their equivalent weights. This result leads us directly to Faraday's second law of electrolysis. Thus, according to Faraday's second law of electrolysis, if the same quantity of electricity is passed through different electrolytic cells containing different electrolytes, the amounts of substances formed are directly proportional to their equivalent weights. Now, once again, let us revisit the concept of equivalent weight. For elements, the equivalent weight is given by atomic weight divided by valency. This relation will be very useful while solving numerical problems based on Faraday's laws of electrolysis. Now let us solve a numerical problem. Calculate the mass of copper deposited at cathode when 400 coulombs of electricity is passed through an aqueous solution of copper sulfate. During electrolysis, copper 2 plus ions are reduced at the cathode to metallic copper. Therefore, the valency of copper is 2. Hence, the equivalent weight of copper is given by atomic weight divided by 2, that is equal to 63.546 divided by 2. Hence, the equivalent weight of copper is 31.773 grams. Now, using the relation MCU is equal to ECU into Q divided by F, and substituting the values of E, that is equal to 31.773 grams, and Q is equal to 400 coulombs, and F is equal to 96,500 coulombs, we get 0.1317 grams of copper, and this is the mass of copper deposited at the cathode. Now another problem based on Faraday's second law. During the electrolysis of an aqueous solution of copper sulfate, 63.546 grams of copper is deposited at cathode. What will be the amount of zinc deposited when same amount of electricity is passed through an aqueous solution of zinc sulfate? We can solve this problem by using the relation obtained from Faraday's second law of electrolysis. According to Faraday's second law, we can write mass of zinc divided by mass of copper is equal to equivalent weight of zinc divided by equivalent weight of copper. And by substituting the equivalent weights of zinc and copper into the above relation, we obtain mass of zinc deposited equals to 65.38 grams. That's all for now. Visit adichemistry.com for more information on this topic or search for Adichemistry Faraday's laws by using any search engine. Don't forget to like, share and subscribe.